Hello everyone, welcome to the Kinematics and Dynamics of Machinery class. In today's video, we're gonna discuss the kinematics of direct and rolling contacts problem. This is like a special type of problems that or cases that we would experience in some mechanism that you do have some objects that already slide or just in direct contact or in rolling contact to each other during during the mechanism motion. So it is highly important through this class to know how we can do kinematics and dynamic analysis for these, or kinematic and kinetic analysis of these mechanisms that would include some objects that they already, or elements that they already in contact. So generally we do have two different types of contacts that we are going to cover here. The first type is the direct contact, and the second type is the rolling contact problem. So in the beginning, I'm gonna start with the direct contact, and then we're gonna discuss the rolling contact. The direct contact, in this type, we will find a slider that slides over a surface which is either straight or curved surface. Like, for example, like these cases. All of these cases are different cases of direct contact, and we had covered this one before. So what are the objects that they already in contact? We do have here the slider that slides over this surface. We do have this slider that slides over this surface. So there should be contact between the slider and the surface itself. There should be contact between the slider and the surface, and so on. But for this type here, or for this case, we probably have the slider that slides over a curved surface like this one, or it would be moving or sliding over a fixed a straight surface like this case, or a curved surface like this case. So whatever the type of the surface that we have, so here we have a direct contact. It means that we have an object that is in contact with another object, and the one is sliding with respect to the other one. So there is a relative sliding motion between these two objects. So we're gonna say that this type of contact is a direct contact problem. All right. The other type that would have a roller, like we do have a roller that really rolls over a surface. So this is a contact. This is one type of the contact problem, but this is commonly known as the rolling contact. Rolling, it means that there is no sliding, there is no slipping over the surface, as we are going to discuss. So in the beginning, we're gonna start with the direct contact problem, and this type of problem we can classify it into two different types. So again, we're gonna start with the direct contact. The direct contact means that you have a slider or an object that slides. So there should be sliding motion. There should be slipping. There should be relative movement of one object with respect to the other one. But in the rolling contact problem, there is no this relative movement. There is no slipping. The only possible motion is rolling. This is the other type of problem, which is the rolling contact problem. If we focus on the direct contact problem, we do have two different types. And the first one, that you have a slider that moves over a fixed surface, or an object that slides with respect to another object, but the other object is fixed. Like a slider moving over a fixed surface, whatever this surface is a straight surface like these cases, and we already covered these types of problem before. Or you do have, and this is the new thing here, how about if you do have this surface is not straight, it is curved, how we can handle or deal with this type of problem as direct contact problem. This is also what we are going to cover. In case that you would have the surface is not movable, I mean that this ground or this surface is not movable. So in this case, for this type of problem, we won't gonna end up with any carrier acceleration. If we did the position analysis, then velocity analysis, and then we move to the acceleration analysis, we're gonna find that the acceleration equation, it will not include any carrier acceleration. Why? Because that this surface is a fixed surface. This is fixed, it is immovable surface. The same thing for this one is a fixed surface. As I mentioned, we already discussed these two types of problems before. But here the focus in this part is over these types of problem in case that we do have curved surfaces. We have give a hint about the curved surface and the graphical solution of this type of problem, but we even didn't cover this one in that part. So, and that's why the focus basically is going to be over this type of problem. How about if we do have a curved surface, how we can deal with it or solve this type of problem? This is what we are going to discuss through this video. The second type of the direct contact problem, that we would have the surface itself or over one or the two objects already movable. Like we said that in direct contact we should have two objects and one moves with respect to the other one. If there is one of the two objects is already fixed, so this is the first type of the direct problem. The second type, that you'd have the two objects, both of them are moving, but there is still a relative movement between them. What does it mean? It means that the first object, it should be moving with a displacement, velocity, and acceleration that totally different than the other object. So there should be some relative velocity and acceleration between them. This is typically like the case that we have a slider moving over a rotating rod. Like this rod is already rotating here, right? And there is a contact over this surface between the slider and the rod itself or the link itself. So this link is already movable, it moves, and the slider in the meanwhile also it moves. So this is the slider, it doing sliding motion over the link. We already covered this type of problem in the class, right? We already covered this one and we knew how we can handle or solve this type of problem analytically and graphically. But how about if we do have this link, it is not straight? How about if it is already curved? We said that this link, it will have a radius of curvature, and this radius of curvature that we used to or agreed to give it a name like rho, this rho will have a specific value, but here rho is tends to infinity. So that's why if you remember in the graphical solution, the normal acceleration was 0 because it should be the sliding velocity squared, the square of the sliding velocity divided by the rho, which is the radius of curvature of this length. Since it is straight, so rho we agreed that this rho is going to be tends to infinity. But in case that the link is already rotating like this one and the slider is already sliding over a curved link, so in this case we do have a specific value for rho, and for this case we're going to end up with a Carolus acceleration. For this type of problem, as we agreed before, that we end up with Carolus acceleration already showing up in this type of problem, the same thing is gonna be happen to this one. So the focus through this video or this type of problem is all on this type of problem, that you'd have the link, it is not straight because we already covered this one. Now we're gonna focus and we're gonna know how we can handle the case that you'd have the curve, the link is already curved. The same thing, for example, one of the important application, and this is what we're going to cover the next topic, which is the cam design or the cam mechanism. The cam mechanism, that you'd have a cam and there is a follower like this one, and we're going to discuss these two components or this type of mechanism with more details when we discuss the cams. But anyway, like assume that this is a cam with a specific profile and there is a fixed point, and this cam, it should be rotating about this fixed point, and this is the follower also, it is pivoted at this point and it can rotate, but it follow all the time. It should be in direct contact at this point. So this is the contact point, this is the contact point between the follower and the cam. So I do have two objects that they already in contact, and one slide with respect to the other one, or in other words, both are moving. So there is a relative movement between them, right? So this is the second type of the direct contact. In the first type, as we mentioned, one of the objects should be fixed, immovable, but here we should have both objects already rotating as this case. Also, like this case, we do have, this is also a cam, this is another type of or profile of the cam, and these two like different followers. So as you can see here, this is the contact point. Here we do have a different contact point over the cam. And as long as this cam is already moving or rotating, these followers somehow they gonna be rotating. This follower and this one, both they gonna be rotating at these fixed points. And this is the point of rotation of this cam. So we do have two different objects, or in this problem we do have three objects. But we can handle this problem like two separate problems. Like we can consider this follower with the cam in one problem and this follower with the cam in another problem, kind of. So yes, so in this type of problem, as I mentioned, we do have these two objects that they already in contact at a specific point or over a surface. In many of the cases, it's gonna be just contact over a surface, like this case. And there should be definitely some sliding, like one object slides with respect to the other one, but the two objects are moving. So this is the second type of the direct contact problem. Very similar to this case that we do have, this is all of this part is a single object, and this is another object. So it means that we do have two objects or two lengths kind of, but these two lengths, they do have specific shapes. So this one is moving and this one also is moving, and this is the point of contact between them. So this is another type, or the second type of the direct contact problem. For all of these different types, the common between them is that there is a curious acceleration that it shall be obtained when we try to do the acceleration analysis of any one of these different types of problems, or according to the direct contact. So this is the second group. The first group, you could say that there is no curious acceleration, and this happens only if in case that we do have one of the two objects that they already in contact is fixed, and the most common case that you'd have a slider that moves over a surface, whatever fixed surface. The second type, you're gonna have the two objects that they already in motion, both of them are rotating or moving, and in this case definitely we're gonna end up with some curious acceleration. Make sense? Now let us discuss some things about the two different types that we discussed so far in the direct contact. Now we still focus on the direct contact. We didn't move yet to the rolling contact. So I'm gonna finish the direct contact first, and I'm gonna show you through this video how we can analytically solve these direct contact or rolling contact problems using the complex algebraic method. So in this video, we're just gonna focus on the analytical solution. Then in another video, I'm gonna show you how we can do it graphically. So in the first step, as I mentioned, if you remember, we stated that there is no, for the first time, there is no curious acceleration, right? And like this type of problem, this is what we covered. So what we already discussed, like we do have this slider. If we just consider, let me highlight the main mechanism. So the main mechanism is already as follows. Like we do have a link, and then there is another link, and there is a slider that already moves over this straight surface. And this surface is already straight. It means that its radius of curvature tends to infinity, and it is fixed in the meanwhile. It is not movable. So that's why it is located in the first type. Like this is the problem how it was given. It was given to us as two lengths, and there is a slider moving over this surface. As we discussed before, it doesn't matter whatever this surface is, horizontal surface, vertical surface, inclined surface, even, you just gonna follow the same procedure. And if you remember, we agreed that to solve this type of problem, we have to define some analytically, we have to do some position vectors, then we're gonna form the loop closure equation. And the key idea is to investigate which one of these position vectors with fixed or constant value of magnitude, or variable or constant value of direction. It means that you have to investigate the direction and the magnitude of each one of these position vector. Which one is constant, which one is variable over time. Like this case, I'm gonna assume that I do have R2 as position vector for this length number 2, and we do have another length, so this is gonna give us R3. Then we do have a slider, and we agreed before that for any slider, for the slider, we should set up a position vector, that this position vector, it should be going to the slider sticking to the same direction of motion. This is what we already discussed before, right? Over the surface. This slider already sliding over this surface. This is the direction. So I'm gonna assume a position vector R that already going to the slider. And if we did so, we're gonna end up with one position vector. Then there is another position vector, which is R3. Then there is R4. So we're gonna end up with an open loop. We have to close this loop using this R1. So I'm gonna close this loop with the R1. With this R1 is just an arbitrary position vector. As I mentioned, we have defined this one to close the loop, and we're gonna end up with a point here. You should understand, if we give a name to this point, like point O, you should understand that this point O is a fixed point. It is not movable point, and you could consider that this is a reference point from which that this slider is going to slide up or down. Make sense? So then if we decided to investigate which one of these R1, R2, R3, and R4, also theta 1, theta 2, theta 3, and theta 4, which one of these parameters already fixed or constant with constant value, which one is changing over time? So for R1, for example, do you think that this R1 distance, do you think that it's going to change over time? No. Why? Because the slider is just sliding up or down. It doesn't matter where is the location of the slider. This distance between point O and this fixed point is going to be a fixed distance. So in this case, we do have this R1 is a constant. The same thing for theta 1, because R1 vector, this vector, it won't gonna rotate. There is no possible rotation for this one. So this is like the frame. This is because it is set up between two fixed points. This is a fixed point, and there is another fixed point here, right? So what does it mean? This indicates that theta 1, it should be constant as well. But how about R2? R2, it should be constant as we discussed before, because this R2 refers to the length of the link, and this link it is with a fixed length, and the theta 2, which it should be this angle, is gonna be variable. It means that this gonna be varying over time. But R3 also is gonna be constant, but theta 3 is gonna be variable. Why? Because this link is going to rotate, right? And if we have a look to the R4, R4 itself is going to be variable, because this distance, R4, it should be the distance between point O and the slider itself, and the slider really slides over the surface. So as it goes up, R4 is going to increase, goes down, R4 is going to decrease. So what does it mean? This indicates that R4, it should be variable, but theta 4 definitely is going to be constant. Because why? Because this is a straight curve or a straight surface, and the slider, there is no possibility for this R4 to rotate. This is what we already discussed before, and nothing new so far, right? But this type of problem can be classified as direct type problem or direct contact problem that belong to type 1, where if you remember, when we solve a similar problem, we didn't end up, or we didn't get any careless acceleration, right? This is very similar like this problem. We do have a slider, that this slider already slides over a straight surface like this one, and again rho, which is the radius of curvature of this slider, already tends to infinity, right? And we do have one link, and we do have another link. This is the conventional slider crank mechanism, and there is R1, which should be like an offset distance. And we used to define like R2, this is a position vector, there is another position vector that over this link, and we have to set up R4 in the direction of motion of the slider, and this R4 should be going to the slider as we agreed before. Then we can set up R1. It doesn't matter the direction of R1, up or down. Anyway, it is set up between two fixed points, and we can give a name to this point like point O, for example. And if you remember that we agreed for this type of problem like R1 and theta 1, then R2, R3, and R4, then the theta 2, theta 3, and the theta 4. Which one is constant, which one is variable? This is what we discussed, what we already discussed before. For example, R1, it should be constant, right? And theta 1 also should be constant. Why? Because this is a fixed link, this offset distance. And R2, it should be constant, but theta 2 is going to be variable, because this link R2 is going to rotate. The same thing for R3, it's going to be constant, but theta 3 is going to be variable. For this case, we do have R4 is variable, is changing over time, but theta 4 is going to be constant, right? So as you can see, also in this case, there is no careless acceleration, because the careless acceleration, the key idea that you should have a vector, a position vector with both R and theta are variables. But here, in this case, we don't have either R or theta is variable. Like this case, we have either R or theta is variable. So that's why there is no carrier acceleration is going to show up here. And the main reason behind this actually is that this surface over which this slider is already sliding is a fixed surface. How about, so we already discussed these two different cases. How about if we do have the same problem, very similar to this one, but we're gonna do a little bit small change here that just make this surface, and instead of being straight, we're gonna make this surface as curved surface. Like assume that this slider is already sliding over a hill or a curved surface or whatever, right? So, and this is typically is gonna be like this case, like we do have this crank. This is the mechanism. What I'm presenting here is the mechanism, and this is the fixed point. And there is a link, and there is a slider. And this slider is already sliding over a curved surface like this one. With this curved surface, it will have a radius of curvature rho, where rho in this case will be given a value. It won't gonna be infinity anymore. It will be with a specific value. This is the rho. So how we can solve this? This is a new thing. This is a new type of problem, which it should be slider. This is also slider crank mechanism, like the conventional mechanism up there, slider crank mechanism. But the new thing, as I mentioned, that this slider is really sliding over a curved surface. In case that we do have a curved surface, so this is, we have to handle this problem like a direct contact, because there is already direct contact problem, because we do have the slider already sliding over a fixed surface, and it means that there is a relative movement between these two objects, and this is the first type of the direct contact. It means still in this problem there is no carrier acceleration. Why? The surface over which the slider slides is fixed surface, so there is no carrier acceleration that is gonna be obtained when we do acceleration analysis to this problem. But what is the new thing here? If you compare this problem to this one, if you remember, the difference is gonna be how you define R4, or how you define the position vector for the slider. Since the slider here is already moving over a straight surface, we agreed to define R as a position vector over the same direction of motion, or the line of sliding of the slider and going to the slider. Like this case, I do have the slider is moving horizontal, so I defined R4 to be going to the slider horizontal as well. In this case, we do have the slider sliding over inclined surface, so I defined R4 over the line or the sliding motion, the line of the sliding motion of the slider going to the slider. But here, this slider has no specific line of sliding. Why? Because this slider at this instant of time is already here. After a while, it's gonna be here. So it's sliding, it slides over a curve. It is not sliding over a straight line. So it is not possible to connect one of the things. For example, I can connect this point to this point directly, but this R is gonna be movable. This R, it won't gonna be fixed. So how we can handle this type of problem? You have to set up for this type of problem, in case that you have a slider sliding over a curved surface, you have to set up a position vector between the center point. What is this C? C, this is the point, the center point of the curvature of the curved surface. This curved surface, it should be like a circle, right? Like a sector of a circle. And this circle, it should have a center point. So this is the center point. Your objective is just to set up a position vector between the center point and the slider itself. This is an important position vector that should be defined. And this position vector, it's going to represent the slider in this case, or one of the vectors that is going to represent the slider. Make sense? So what is the difference between this case and this case? Here, the surface was straight, so we used to define R4 in the line of action of the slider going to the slider. But in case that we do have a curved surface, one of the essential position vectors that you have to set up is the position vector between the center point of the curve and the slider itself. So if I decided to work over this problem, what should be the position vector that you are going to set up? Initially, you're gonna assume that we do have R2. This is the position vector for this link. And we do have another link, so we shall set up another position vector as R3. Then we do have a slider, so I have to define a position vector for the slider. But the problem is that this slider is movable over a curved surface. So there is an essential or a position vector that we have to set up between the center point of the curve of the surface to the slider itself. This is gonna give us R4. So as you can see, we end up with open loop, 3 vectors, but the loop is still open. So that's why I'm going to set up here R1 to close the gap. Where R1 is gonna be between 2 fixed points. You should understand that this point C is a fixed point. Why point C? The center of the curve is fixed. Why? The main reason is because the surface, the curved surface is fixed. So definitely this point it won't gonna move. Why? Because the surface itself, it is a fixed surface. Make sense? So this is a new thing, right? In case that you have a slider moves over a curved surface, there is an essential position vector that should be set up between a fixed point, which it should be the center of the curve, as long as the surface is already fixed. And this is the first type of the direct contact problem, and the slider itself. If we set up R2, R3, and R4, where R4 is gonna work for the slider in this case, we won't gonna able to define R4 that is already over the sliding motion of the slider. Why? Because simply the slider moves over a curve. There is no straight path over what that this slider is already moving to set up R going to the slider, as we used to do for the previous case. So here we have to define an essential position vector between the center point and the slider R4. If we set up R2, R3, R4, we're gonna end up with an open loop. We have to close this loop with R1 that connect the fixed point to the center point. And you should understand that this center point is a fixed point, like typically like this one. Why? Because the surface is not moving. So if we decided to define the R1, R2, R3 and R4 for this case, and also theta 1, theta 2, theta 3 and theta 4, which one is variable, which one is constant? So for this problem, R1 definitely is gonna be constant. Why? Because R1 it is set up between 2 fixed points. This C is not moving, this point also is not moving. Also theta 1 is gonna be constant. What? This R1 it won't gonna rotate. But how about R2? R2, the length of the link, it should be definitely fixed length, but theta 2 is gonna be variable. And theta 2, if you remember, it should be this angle. This angle, it should be theta 2. Theta 3, it should be from the start point going counterclockwise, so this is gonna give us theta 3. And for the R3 is gonna be constant, but theta 3 is gonna be variable, changing over time. Make sense? How about R4? This is a new position vector, right? R4, it should be the distance between point C and the slider itself. Do you think that this distance, which is R1, forget about theta, is it fixed or variable? It is constant. Is it constant or variable? If you just observe this one, you're gonna find that it is constant value. Why it is constant value? Because R4 here represents rho. R4 in this case, and this is a new thing, R4 equals rho, and all the time is gonna be constant. What does it mean, rho? For example, assume that this slider has been moved to this point. So what should be this distance? This should be R4 as well. This R4 is gonna be still rho, the radius of the curvature, right, which is already given. And if the slider has been moved to the right, you still have this distance as R4, which is rho, which is the radius of the curvature. So all the time for this case, R4, which is the position vector that you're gonna set up between the center point, which it should be fixed point, and the slider, this R, the magnitude of this position vector all the time is gonna be constant and equal the radius of the curvature of the curve. But theta is gonna be variable. Why? Because the slider, if the slider moves to this point, you're gonna find R4 has been rotated with an angle. This is the angle. If it has been moved to the right, it's going to rotate in this direction. So what does it mean? This means that theta 4 is gonna be variable in this case. As you can see, there is no carriers acceleration. There is no carriers acceleration. Why? Because there is no acceleration. Why? Because there is no position vector that have both r and theta are variable. You'd have either r or theta is variable, but we don't have any position vector here had both r and theta are variable. So that's why we still will not end up with any careless acceleration when we do acceleration analysis for this mechanism. Why? The main reason is that this surface is a fixed surface. Make sense? So this is this is the focus of this video actually, how we can handle this type of problem that include a slider that slides over a surface, and this is the first type of the direct contact problem. Also another thing, if you can observe the difference between this problem and the previous one for the R4. R4, it has been defined, we defined R4 as a position vector to describe the motion and the velocity and the acceleration of the slider. Here R4, it has been defined, this R4 also it had been defined to define the velocity and the acceleration and the movement of the slider. So still R4 works for the slider, R4 here works for the slider. But if we just compare the R4 to this R4, R4 here for this slider, it has R is variable, but theta is constant. But here we have the opposite. R is constant, theta is variable. But we still have no careless acceleration. So this is a different case. This is the first time that you have R4 for a slider with R is constant, but theta is variable. How about this case? It's gonna be very similar. This is the mechanism that already given to us. We do have this crank. This is the crank of the slide of the mechanism, and this is a connecting link. And we do have the slider. This is slider already sliding over a curved surface. So this is the surface here. And definitely this curved surface will have a specific radius of curvature where this is the center point. It is highly important to acknowledge or define the center point of the curvature. And you should understand that this center point, it is fixed as long as the surface is immovable or it is fixed surface. So how we can define the different position vectors for this mechanism? Definitely we're gonna define R1 as for the link, and then we're gonna define R3 for the connecting link, which is R3. So we do have R2 and R3. Then how about the slider? Unfortunately, the slider is not moving over a straight surface, so we cannot set up a position vector for the slider that already over its sliding motion because it slides over a curve. So instead we have to define a position vector for the slider. This position vector, it should be set up between the center point of the curvature and the slider itself. So I'm gonna define R4 for the slider. So as you can see, we do have R2, R3, and R4. So it is open loop, it is not closed. To close the loop, we have to arbitrarily assume another R, which is gonna be R1, this one, R1. And this R1, it should be set up between the fixed point in the mechanism and the center point of the curvature, which should be fixed point. As we mentioned, why? Because the surface itself is not moving, but the slider slides. So we're gonna end up with a 4-bar linkage or 4 position vectors. If we decided to investigate which one of these R's and thetas are constants, which ones are variables. So we're gonna end up with typically the same things that we discussed up there. It means that this mechanism is typically the same like this mechanism, but you could consider that this is a different configuration of the mechanism. R1, it should be the distance between O, which is this fixed point, and point C. So it means definitely it's gonna be constant, while this fixed distance is just constant distance. Theta 1 is gonna be constant as well because there is no possibility for R1 to rotate. R2, it should be the length of R2, which it should be constant. Theta 2, it's gonna be variable because definitely this R2 is going to rotate. The same thing for R3 is gonna be constant. Theta 3 is gonna be variable. But the R4, this is the new thing. R4, it should be fixed, equals rho, and it should be constant all the time. Why? Because the distance between C and the slider, and the slider moves over a curved surface. So no matter what, where is the location of the slider over the surface. If you try to connect the slider to the center point C, you're gonna end up this distance all the time it is rho. This is like rotating over the circumference of a circle with a radius rho. So definitely R4 is gonna be constant, but definitely theta 4 is gonna be variable. It makes sense? So this is the first type of the problem. Why I'm explaining these things, especially for these two new cases. Basically, as we agreed before for the analytical solution, your objective is just to set up some position vector and investigate the values of these r's and thetas, which one is variable, which one is constant. Then once you do this, forget about the problem totally, and you're gonna stick to a fixed procedure. Form the loop corrosion equation, solve this loop corrosion equation, then you're gonna form another loop corrosion equation for the velocity by the derivative, then the acceleration. It means that the rest of the problem is gonna be fixed procedure, nothing new. The new thing, how you define these r's and thetas, which one is constant, which one is variable, and how you set up these position vectors. In case that you do have a slider that slides over a curved surface like this type of problem or this case. But the rest of the problem is going to be fixed procedure as we discussed and we practiced many times before over the analytical solution using the complex algebraic method. Make sense? So this is the first type of the direct contact problem. Now let us move to the type 2, the second type of the direct contact problem. So let us consider this mechanism of the cam and follower mechanism, that this cam is rotating and the follower is gonna just follow the rotation of the cam, and there is a point here. Let us give this point a name as point B, where this point B should be the point of contact, that is should be a common point between the follower and the cam. And the good thing or the important notice that you should observe about this point B, that this point P that belongs to the follower all the time is going to be a fixed point with respect to the follower, but it's going to be changeable point with respect to the cam, as I'm going to show you. So for example, just to understand how this cam mechanism is working, what I'm going to do here, I'm just going to assume that this cam is going to rotate in this direction. And if we give a rotation to this cam in this direction, after a while, the cam is going to be somewhere because it has a specific profile. So I'm gonna just show you how it's gonna look like, the cam itself. So assume that we give a rotation to the cam. What should happen at this instant of time to the follower? The follower is gonna have some kind of rotation. It will start to rotate and it's gonna rotate up. The important point here, or the important thing that you should observe, that this point of contact between the follower and the cam, it will not be changing with respect to the follower. So what does it mean this? It means that the distance of this point P and point O over the follower, this distance, it will not be changing at any instant of time. This point, it will be fixed all the time. Try to imagine this. Try to imagine the rotation of the cam, and the follower follows, it is follower to the cam. It follows the motion of the cam. As we give rotation to the cam, the cam mechanism or the cam itself, this point that belongs to the follower, but the point that belongs to the cam is going to change definitely. But I'm talking about the point that belongs to the follower. After a while, this point will be still the same with respect to the follower. So what does it mean? It means that the follower all the time touches the cam at any point that belongs to the cam, but at fixed one fixed point with respect to the follower. Mean that the follower touches or in contact with the cam at only one point, which is this point B. And this point is a fixed point. It is not changeable with respect to the follower, but it is going to change with respect to the cam. Make sense? So this is the cam mechanism at a certain instant or for certain degrees of rotation. But if we continue the rotation of the cam 390 degrees, definitely this point is going to change. Here we're gonna assume this case that we do have the angle of rotation, it is not that big. For a small rotation of the cam and the follower, this point of rotation or this point of contact that belongs to the follower is gonna be a fixed point. We're just gonna consider this case. But definitely if the cam continue the rotation, the 360 degree, definitely this point that belongs to the follower is going to change. But here I'm talking about this very small arc, over this small arc with a small angle of rotation. This angle of rotation, if it is too small, if it is small angle of rotation, so this point B will be a fixed point with respect to the follower. Make sense? Try to imagine this, you're gonna realize this fact. As long as this angle of rotation of the cam with respect to the follower, it is not a big point, right? Or at the angle of rotation, it is not big angle, just small angle of rotation. So in this case, we're gonna find that this point B will be the same point of contact with respect to the follower. Make sense? So going back again to this mechanism, and we are interested to set up some position vectors as to solve this mechanism. So basically, since we don't have a follower, this follower works like a link. So definitely if we connect point P that belongs to the follower to the point of rotation, this is gonna give us a position vector, right? And so this is one position vector. Forget about the number. Let us assume that the cam is given number 2 as element number 2, and this is link number 3 or 4 or whatever, like this is 4. Okay, so I'm gonna set up here R4, which is just a position vector for this link from the fixed point going to the other point, which is this point B. This is our more concern. We don't care about the extension of the follower, we just care about the point P itself. Then for this is a second type of, this is the second type of direct contact problem. We said that in the direct contact we should have two objects that they already in contact together. We have these two objects here, which are the cam and the follower definitely, and they already in contact at point P. Make sense? So this is a direct contact problem, but a second type. The second type, why? Because both options that they already in contact, both of them are rotating. Both of them are moving. There is no fixed objects here, right? In this case. So what does it mean? It means that if we try to solve this type of problem, we shall end up with a curious acceleration. Definitely, that's why it is grouped as type 2. Make sense? So this cam is going to rotate, the same thing for the follower. So for this type of problem, in case that you don't have a cam or this, you have to connect the fixed point to the tangent point or the contact point, and connect the fixed point to the contact point to set up two position vectors. So now I'm gonna set up two position vectors between the fixed point for the first object that already rotating to the tangent point, and between the fixed point of the second object that already rotating to the tangent point. Point B is a common point between both of them, the mechanism and the cam and the follower. So I set up R2. Why I give this one R2? Because the cam was given a number as 2 and the follower was given a number as 4, so I give it like R4. So R4, this is a position vector connected between the fixed point of the link or the follower, which is one of the objects that already in contact, to the contact point, and then I did the same for the other object, which is I connected or set up R2 for the cam, which is the other object that already in contact from the fixed point to the point of contact. So we're gonna end up with a loop, but this loop is already open. So to close the loop, we have to set up here or assume this R as R1 position vector. So we're gonna end up with this loop that includes three position vectors, R1 set up between two fixed points, the fixed point of the first object and the fixed point of the second object, and R4 and R2, which are the two position vectors. You should understand that this position vector R2, it works for the cam. So R2, it will describe the rotation, it will describe the movement of the cam, it will describe the velocity and the acceleration of the cam. But R4 is going to describe the velocity and acceleration and the movement of the follower or the link number 4. Make sense? So then if we decided to investigate which one of these R's and thetas is fixed or constant, which one is variable, like theta 1, R1, R2, theta 2, and R3, theta 3. And this is the most important part. These two parts here, just to define the position vectors, how you define them, how you define these R's and thetas, which one is constant, which one is variable, is the most important. This is the start of the problem. If you did this one correctly, the rest of the procedure is just a fixed procedure. You have three loops, three position vectors, closed loop, form the loop Recursion equation and work. Stick to the procedure, typically the same procedure that we explained before. So how about R1? R1, it is set up between two fixed points. So definitely R1, it should be constant. And theta 1 also should be constant. Why? It is this link, it won't gonna rotate. R1, it is a fixed length. And how about R2 and R4? This is the tricky part. R2 is gonna be variable. This is something that you should understand. Why? Because as I mentioned, if we give rotation to this cam in this direction, for example, after a while the cam is gonna be oriented. Assume the cam had been oriented in this direction. So the follower is going to rotate down. This is the new location. Assume that this is the new position of the cam and this is the new position of the follower. So this point of contact, this is still the point of contact, which is point P, and R2 all the time it is set up between point P and the fixed point. So as you can see, R2 became shorter. R2, it became shorter. So what does it mean? It means that R2 itself, the length, it should be changing over time. Make sense? How about theta 2? Also, is going to rotate. R2 is going to rotate after a while as long as the cam is rotating. So it means that theta 2 also is going to be variable. Make sense? So theta 2, it will be variable. But how about R3, R4? We don't have here 3. R4 and theta 4, which are for the R4. R4, which is this position vector that's set up between this point B and the fixed point, right? This distance, it won't gonna be changing. This is something that you should understand. This is what I meant to say here. It's just that this distance all the time, it should be fixed distance. Why? Because all the time point B will be the same point with respect to the follower, but it will be a different point with respect to the cam. So that's why R2, the length of R2 became shorter or longer, depends on the direction or the position of the cam with respect to the follower. But this distance between point P and the fixed point of the follower, it will be a fixed point. So it means that R4 in this case will be constant. But definitely theta 4, it will be variable because this link has been rotated. Make sense? This is something highly important that you should understand about this cam follower mechanism. Like the R2, as we mentioned, will be variable because after a while this is going to rotate and change. So R2 and theta 2 for the cam both will be variables. And R4, theta 4 only will be variable, but R4 will be constant. This is something that you should understand about this mechanism. As you can see, since we do have R and theta, both are variable for the same position vector, definitely we will end up with Carolus acceleration. Why? Because we do have R and theta for the same position vector is our variables. If you stick to the procedure and apply the algebraic solution using the complex method, we're gonna end up directly, definitely in the acceleration analysis part with a Carolus acceleration. Make sense? It is highly important to understand that point P for the follower, it will be the same point, but it will be a different point with respect to the cam, and that's why for this case R2 is variable and theta 2 is variable, but R4 is constant, theta 4 is the one that is already changing over time. Make sense? This is for this mechanism, which belongs to the second case, second type of the direct contact. Because of what? Because of the the Carolus acceleration, which is going to be is gonna show up. Now let us move to this mechanism and do the same. This is we have considered this one before, but the only difference in this case that this link, it is curved. It is not straight like the previous case. So I'm gonna show you something interesting here. So how we can set up the position vector, and this is the first step. Let us assume give some number. This is like the frame, and we do have length 2, and we do have length 3 in addition to the slider itself, which is like object 4. All right. Then what we're gonna do, we're gonna set up some position vector. Definitely we're gonna define a position vector over this length 2 to be R2. So this is the R2 vector. Now we do have length 3, but the problem is length 3 is a curved length. It is not a straight length to set up R for this length that goes over the length itself. It is curved. So it is not possible to have a curved position vector. It doesn't make sense. The position vector should be straight position vector, and the length is curved, so we're gonna able to set up at the moment, we're gonna able to set up a position vector for this length. Just keep this length for now. The same thing applies for the slider. The slider, it slides over a curvature. So if you remember in the first type, we said that in case that would have a slider that moves over a curved surface, there is an arbitrary position vector that should be defined for the slider, and this position vector, it should be set up between the slider and the center point of the curvature, right? This is what we did here for the first type up there, right? In the first type, we said that in case that you have a slider that slides over a curved surface, there is R4. This arbitrary position vector should be set up or defined between the slider and the center point of the curvature to define the position or velocity and acceleration for the slider. So this R4 is going to work for the slider. I'm going to do the same here. No matter what this curved surface, the slider now it moves over this curvature or over this curved surface. So I don't care whatever this surface is moving or fixed. I'm gonna do the same as I did before. I'm gonna define here from this point, which is the slider itself, and the center point. Assume that the center point of this curve is somewhere here. We don't know exactly where is this center point. Like this case, this center point definitely will be given. Why? It is a fixed point. But the problem why it is fixed, because this curvature is fixed point, is fixed surface. But here, the center point, this center point C, it's gonna be movable point. It will not be movable. Why? Because the length itself is rotating. So there is no specific location for point C. So that's why this point C will not be given. But for this previous example, for this case one, this point C will be defined and it will be provided and it will be given to you in the problem. But point C for this length, it will not be given. So assume any location of this point, assume any arbitrary location of this point just to set up the position vectors, but you should understand over which side. Since it is curved here, definitely it should be on the left of the length, and it should be somewhere into this region. So let us assume that this is point C. Then what you're gonna do, you have to define a position vector that is set up between the center point and the length itself, or the slider, I'm sorry. This is gonna be R4, and this R4 is gonna work for the slider. This R4 is gonna describe the velocity and the acceleration and the position of the slider 4. But R2, it works for the length. There is a length here. Make sense? So now we do have R2 and R4, the loop is still open, and we have to define another R3 for the length number 3, right? Now if you connect the fixed point of the length to the center point of the curvature, we're gonna end up with R3 vector. We're gonna end up with R3 vector, which is this one. You should understand that this is R2, then we do have R3, we do have R4. So the loop is still open. If we try to move R2, R4, R3, the loop is still open. To close the loop, we have to close this loop with this position vector as R1 vector. So you're gonna work like you're already moving in this direction. R1, R1, then R3, then R4, then R2. Right? This is the loop. It has 4 position vectors. It makes sense? You should understand that R3, it works for the length number 3. Why I didn't connect this one to this one directly and define this R to be for both the slider and the length? No, it won't gonna work in this way. Why? Because the slider requires a position vector that is set up between the slider and the center point of the curvature over which the slider is already moving. So R4, it should be arbitrarily assumed for this slider. Then to close the loop, R3 is gonna be set up as well for the length that rotates. It should be set up between the fixed point and the center point of the curvature of the same length. Make sense? There is an interesting thing here that I'm gonna show you. Assume that this point, assume that this length, now because this length is already curvature, we're gonna end up with this like sector of a circle, right? This shape. And if you consider that these two parts, these two lines, this line and this line, like two stick, and if you try to straighten or make this length straight, if we try to make this length straight, you're gonna find that this point is gonna be pushed up, this point like is gonna be pushed down somehow. Forget about that this point, in fact, it is fixed point. But if I ask you to unfold or make this length straight and you try to push in this side, this point is gonna move up till the moment that you're gonna find this point C is gonna be conceded to the straight line. If you try to make it straight, you're gonna find this point is gonna be come closer to be sticking here somewhere, and you're gonna find that R4 and R3, both of them, they're gonna be conceded over the straight line for the length itself. Try to measure this case. So what does it mean? It means that in case that would have R4, the length number 3 is a straight length, R4 and R3 will be conceded together because the curvature it tends to infinity. And in this case, R3, it will be conceded over the length, and R4, it will be conceded over the length, and both, they're gonna work for both the length and the slider. And this is what we used to assume in case that would have this length is straight previously. But here we cannot do so. Why? Because we do have this length is curved. So we have to set up two position vectors. One is gonna work for the slider that is set up between the slider and the center point of the curvature, and another one, which is R3, is that is going to work for the length number 3 that is set up between the center point and the point of rotation of length number 3. You should understand that the derivative of length R3, the derivative of R3 gives the velocity and the acceleration for length 3. The derivatives of R4 give the velocity and the acceleration for the slider. Make sense? For this problem, if we decided to work over or define R1, how much, which one is variable, which one is constant. So we do have 4 position vectors, right? R4 and θ1, θ2, θ3, and θ4. So for R1, it should be fixed, it should be constant, right? Why it is set up between two fixed points, definitely the θ1 is going to be constant. R2, how about R2? R2 should be the length of the length. This length OA, for example. This length is a fixed length. So R2 is all the time constant, but θ2 is going to be variable. This is length that do rotation, very simple. But how about R3 and R4? This is the new thing. For R3 and R4, for R3, this thing that you should understand for R3, that R3 is constant. R3 is constant, θ3 is going to be variable. So why R3 is constant but θ3 is variable? How it comes? Basically, as you can see, R3 should be the distance between point C, which is the center point of this curvature, and another point that belongs to the curvature. It means that anyway, this R3 should be rho. It should be the radius of this curvature. Make sense? And this also makes sense if we agreed that R4, which is this one, it should also be constant, equals to rho, which it should be the distance between the center point and the slider, because the slider is already belong to the curvature. So it belong to this curvature or to this surface, and this distance definitely is going to be a fixed point. So R4 also is going to be constant. But θ4 is going to be variable. Why θ4 and θ3 are variable? Because definitely point C is movable point. It is not a fixed point. And even if it is fixed point, the slider is going to slide down, right? The slider is going to slide. It means that this R4 is going to change. And the same thing, if this length number 3 is going to rotate, it means that the orientation or the rotation of the R3 is going to be changing, because definitely, and this is what makes point C moving. So it makes sense that we do have R3 is constant, R4 is constant, θ3 is variable, θ4 is variable, right? But if you observe something here, We said that this is the second case of the second type of the direct contact problem. It means that, and we group this, for this group, we should end up with some careless acceleration, right? One would say that careless acceleration requires or need both r and theta to be variables for the same position vector to end up with a careless acceleration. As you can see, r1 and theta1 are constant, so this one is excluded from the competition. We do have here r3, theta3, and r4. r2 is constant, r3 is constant, r4 is constant. These are variables. So none of these four position vectors would give us a careless acceleration. There is no careless acceleration here. Careless acceleration requires both r and theta to be variables. But we don't have this case. So what does it mean? It means that from the first look, we're gonna say that there is no careless acceleration. So this should be included in type 1 of the direct contact problem. But definitely there is a careless acceleration that is gonna show up for this problem. Why? Because simply this careless acceleration is gonna show up if we try to connect this link. I'm gonna use a different color for this point to this point. This position vector, which I'm gonna give it a name like R5, for example, vector. This R5 has both R and theta are variable, and this is the reason behind the formation of careless acceleration in this problem. Why? Why should we need this R5? Because simply, if I ask you to solve this mechanism, we do have here which one of these will be given, which one will be unknown. You're gonna find that R1, theta1 will be known. It means that this will be with a value, this will be with a value because this distance will be given. Theta1 also is gonna be horizontal, is gonna be 0. R2 it will be given, the length of the link will be given. Theta2 it will be given, which is this angle. So all of these are givens, but none will be given to the R3, R4. Because why? Because point C will not be given, as I told you. In this previous problem, point C will be provided, will be given to you. Why? Because it is a fixed point. But since point C here is a movable point, this point C will not be given. Its location will not be given. Nothing will be given to this point. So we arbitrarily assume this point somewhere depending on the given curvature. It means that the distance from point C to the distance from point C to point A will be provided, will be already given as rho. The distance between point C and point. So R3 is already rho, which is this distance between point C and this point, and R4 is constant. It means that this one will be known because definitely the radius of the curvature will be given, and this one will be known, but theta3 and theta4 will be unknown, right? In this case. So as you can see, we can simply solve this problem, and if we use this loop, these four loops, we shouldn't end up with any careless acceleration, right? But definitely there is a careless acceleration that is gonna show up if we define this R4 vector. As I mentioned, this R4, you're gonna find that this R4 itself, the magnitude is going to change, the direction is going to change because the length is going to rotate, so it will rotate. So theta5 is variable and R5 is variable. So that's why this one has been grouped to type 2 because of the careless acceleration is gonna show up, which shall be shown up in case that we're already defining the R5 for this mechanism. And if we did so, we're gonna end up with the careless acceleration. And even if we apply this one, we're gonna end up with accelerations. We're gonna end up with some accelerations of these two, of the link and of the link number 3 in addition to the slider. When we combine these R3 and R4 together, we're gonna end up with R5, which will be different in terms of variable, in terms of magnitude and direction. And this is the reason behind the careless acceleration, and that's why we already incorporated or including this problem or this type of problem into the second type of the direct problem. Make sense? But basically, if we decided to solve this problem, this one, we're gonna do the same as we did here. We said that you're gonna define a position vector that should be set up between the fixed point and the point of contact, between the fixed point and the point of contact, right? So we have to do the same. So instead of working, if we're gonna work on this problem, we have to set up here, or we gonna set up the R5 between the fixed point and the point of contact, and R2 that is gonna be set up between the fixed point and the R contact to end up with the Cartesian acceleration. Make sense? So it means that if we decided to work this over this problem, I'm gonna say that I do have R1, I do have R2 vector in this way, and R1 vector in this way. So we're gonna end up with this loop that includes R1, R2, and R5. R5 is variable both magnitude and direction, so that's why the Cartesian acceleration is gonna show up, and this is how we're gonna solve this type of problem. Because we are interested in the Cartesian acceleration, and we will not include the R3 and R4 as we mentioned, because simply this point is not given. We arbitrarily assume this one. Make sense? But if you decided to work with R3 and R4, so there is no Cartesian acceleration is gonna show up. If you would set up or used R5, you're gonna find Cartesian acceleration, and this problem can be solved. Why? Because R1 will be fully defined, R2 will be fully defined, but R5 will be unknown, completely unknown. So you're gonna have only two unknowns to that, and this loop can be simply solved. Make sense? There is another example here of this mechanism, but as I mentioned up there, that this is like two problems, not just one problem. It means that we do have here two followers. So, but the problem basically, it's gonna, you will be given a cam, one cam and one follower. Even if you already given this mechanism, you have to handle this one or deal with it like two separate problems. Like for example, if we consider this follower on the top here, this first follower and the cam itself, as we agreed that we have to set up some position vectors, your objective is just to locate the point of contact, which is this point P, for example. Then you're gonna set up a position vector between this point of rotation and point B. And this is gonna be like R2 for the cam. This is the position vector for this cam. Assuming the cam is already number 2, so this is going to be the position vector for the cam as R2 vector. In addition, assuming that this follower is link number 4, for example, so we're going to set up a position vector between this fixed point and the point of contact, very similar to what we did for this cam mechanism up there. Then, in this case, we're going to end up with, this is going to be like R4, or let's say, this is going to be R4 vector. So we're going to end up with open loops that should be closed using this position vector as R1 as a position vector. Make sense? Something that you should observe here, that for this mechanism, it would look like that this point of this is the center point C of this curvature. This point C is the center point of this curvature, right? And as you can see, it would look like that this point C and P, in addition to this point of rotation, all of them are over the same line. But they are, in fact, they shouldn't be. It is not necessary that these 3 points over the same line. Make sense? Especially point C. So you should understand that this point C is somehow shifted into here. For example, like we can set up another position vector for point C with respect to B and point C with respect to point O. So we're going to end up with like another loop, right? We can use this loop for some calculations like the velocity of point P with respect to the center of the curvature, or the movement of this point with respect to the point of rotation. We can set up this loop and work on it. But generally, what we do all the time, connect the contact point to the point of rotation, connect the contact point to the point of rotation, as we did even for this one. Connect the contact point to the point of rotation, connect the contact point to the point of rotation, as we did even for the other cam mechanism. So we're going to end up with this loop. Then we can work on solving this loop by specifying which one is variable, which one is constant. As we did up there, for this mechanism, R1 and R2 R3 or R4. Which one is constant, which one is variable? The same thing for theta 1, theta 2, and theta 3. If we investigated this, R1 is set up between two fixed points, so definitely theta 1 is going to be constant and theta and R1 is going to be constant. Both are constants. And R2 should be the distance between this point O and point P, and this distance is going to be variable. It's going to change. As well as theta 2, it will be variable. Why? Because variable theta 2, it makes sense because the cam is already rotating. So definitely we can understand that R2 is going to rotate. But how come that R2, the magnitude of R2 position vector is going to change? Yes, it's going to change. If you give rotation, this length is going to be shorter or longer depending on the direction of rotation. It means that R2 is going to be variable. Typically the same example that we had here. So as you can see for this example, R2, it will be variable with magnitude and direction for the cam, but R4, it has a magnitude, fixed magnitude, constant magnitude, but variable direction. This is one of the specifications of the cam mechanism. The same thing applies here. R4, which is the point P with respect to the follower, will be a fixed point with respect to the follower, but a changeable, another point or a changing point with respect to the cam. So since it is a fixed point with respect to the follower, so this distance between P and the point of rotation is going to be constant distance, but theta 4 definitely is going to be variable because this follower is going to rotate. How about if we decided to work over the other problem? This is another problem here. So definitely this is going to be the point of contact, which is point P. So I'm going to connect the point of contact to the fixed point. This is going to give us one position vector, and this position vector is going to be set up as R2 for the cam, works for the cam, and we're going to have another position vector that shall be set up between the fixed point and the point of contact. This is going to be R4 for the follower. Then we have to close the loop with another R1 as typically what we did here. So this is going to be the second loop for the other problem, the second problem. And as you can see, R1 as well is going to be constant and theta 1 will be constant because it is set up between two fixed points. R2 is going to be variable, theta 2 will be variable. Why? Because this cam is going to rotate. In addition to this, distance is going to change. If this one, for example, assume that the cam has been rotated down, you're going to find that this distance R2 is going to be is coming shorter. And R4 is going to be fixed point because all the time this point with respect to the follower is going to be the tangent point or the contact point of contact. And theta 4 is going to be variable. So it's going to be the same situation for the other problem. Make sense? Once we define this thing, this is basically the basic concept of the contacts problem. That we do have different types. In some cases, since here, like this case, since we do have variable magnitude and direction to the same position vector, so we're going to end up with the curious acceleration like this one, like this one. So these are the second type. The first type, there is no curious acceleration because you have like fixed, like the case you have a slider that moves over a curved or even a straight surface. We covered the straight surfaces before, so that's why the focus here is going to be over. You have a slider that moves over a curved surface. How we can solve this type of problem? This is the main concern of this or interest of this video. Nothing new except the initial setup of this problem. To set up the position vectors correctly, to specify which one is variable, which one is constant with respect to the time of these parameters, the R and thetas for these different position vectors, then you're gonna stick to the procedure. Apply the procedure as we explained before, you're gonna end up with the position or you're gonna complete the kinematic analysis of this type of problem. And here I'm going to give you this example on the direct and the direct contact problem as an example. Alright, so for this example, it is given a crank, which is crank number 2, and there is a connecting link number 3, and the slider is number 4, and definitely the ground is just 1. But this slider is already sliding over a curved surface as already given here, and the radius of curvature of the curve is given by 300 millimeter, and this is the center point. With this center point, it had been defined, already given to us, with the distance from this center point C to the point O2, this horizontal distance is given by 300 millimeter. In addition to this should stand as rho. This is the radius of curvature as we discussed up there. So this is a direct contact problem. Why? Because we do have two objects that one slide with respect to the other one. There is a relative movement between both, and one of these objects is fixed, stationary, not moving. It means that this is the type 1 of the direct contact problem, and this means that there is no carrier acceleration is going to show up for this example. What is the first step? Just stick to the procedure that we explained before for solving the mechanism, the kinematics of mechanism analytically. The first step is just to set up some position vectors. After giving numbers, and we already give number to the different elements, then your objective is just to set up some position vectors. So definitely I'm going to define here R1, R2, I'm sorry, this is the position vector for this length that do rotation about a fixed point as point O, and it should be projected out of this fixed point. R3, just length that do general beam motion. So you can assume its direction at any direction, like R3, for example, vector, like this case. Then we do have the slider. The slider here is not moving over a straight surface. If it moves over a straight surface, so simply we're gonna connect point O2 to point B, or to define R4 for the slider in this way. But this won't gonna work for this case. Why? Because the slider moving over a curved surface as we mentioned, and we have to define a position vector between the slider and the center point, which is the center point of the curvature. It means that there should be another R going to the slider in this way, moves from the center point to the slider. This is R4. And why R4? Because this R, it has been set up for the slider. It means any time derivative of this R is going to give us the velocity and the acceleration of this slider with respect to this surface. And since the slider had been given a number as 4, so I defined here R4. Now we end up with a loop, but this loop is open loop. To close the loop, I have to connect two fixed points. One fixed point is the center point, which it should be fixed. This is what we discussed before. And another fixed point, which is point O2. So we're going to define here R1 as a vector. So this is the loop that we're going to end up with. As we said before, point C is a fixed point, and we do have R1 set up between these two fixed points, O2 and C, in addition to R4 that had been defined for the slider, and the R3 is defined for length 3, R2 defined for the length number 2. And it is required to find the velocity and the acceleration of points B and A that belong to this mechanism. B, which is point B, which is the sliding velocity and the sliding acceleration of the slider, in addition to point A that we needed for the length that do rotation about point O2. Given that omega 2 is 1 radian per second, where omega 2, this is the direction it goes counterclockwise direction, this is the omega 2, and this angle is already given 60 degrees to define the angle theta 2, in addition to some other directions or dimensions. Also the AB, which is this distance, the length number 3 is already given by 350, and the O2A is already given by 100 millimeters. So these are the given data for this example. Now let us see how we can solve this mechanism analytically using the complex algebraic method. So this is the loop that we set up. We defined R2, we defined R3, we defined the R4 between the center point and point B of the slider, and R1, which is this R that is gonna close the loop, or is gonna close the loop. Now we have to define these different parameters, the R and theta, the magnitude and direction for all of these different position vectors. So let us define them here, starting with R1. How much it is, and theta 1, and R2, theta 2, and then R3, theta 3, and then we do have the R4 and theta 4. You should understand what I'm doing is typically the same thing that we used to do for the analytical solution of any mechanism, but there are some new things that we consider here for the setup of these different position vectors that make this type of problem is a special one in comparison to the previous problem that we considered in the previous meetings. So R1, it should be the distance between O to C. This distance is not clearly given to us, but definitely it is indirectly given. It means that we have to do some trigonometric calculation to end up how much is this R1. One would say that we agreed that don't do any trigonometric calculations unless the count of the unknowns is higher than 2. In this case, we have to do some trigonometric calculation. So it means that I can skip the calculation of R1 first at the moment, but generally speaking, any position vector that is set up between two fixed points in the mechanism, and during the movement of the mechanism, these 2 points all the time they're gonna be fixed. Definitely the locations of these 2 points should be provided to us or should be given. And in this case, the r and the theta of this vector that is set up between 2 points, they should be constants and they should be given. So anyway, it means that since R1 it had been set up between 2 fixed points, R1 will be given with a value, and we can calculate this value the same thing as θ1, and both are constants. But we can skip the θ1 and R1 for now, and let us investigate the R2 and the rest of the other position vectors. R2, it should be the distance between O to A, which is already given up there by 100 millimeter. So the value of R2 is already given by 100 millimeter. But how about is it variable or constant, or is it varying over time? It is definitely constant. Why? Because it refers to the length of the link that it should be fixed during the movement of this mechanism. The same thing for R3. R3 AB distance is already given by 350 millimeter. So this is the value, and definitely is gonna be constant because it is a constant length. But how much is θ2? θ2, it should be as defined here. It should be from the start point, move to the right, rotate counterclockwise direction till you're gonna hit the link itself. This should be θ2. How much it is not given, but θ2, it is given as 60 degrees. So if you added 180 to the 60 degree, which it should be this θ2 as I'm going to define it. So this 60 is already provided to the link number 2 to define the direction of link number 2. So definitely adding 60 plus 180, this is gonna give us the θ2, which will be in this case 240 degrees, and definitely is going to be variable. Why? Because this link is going to rotate, so this should be variable angle. How about θ3? θ3 should be the angle from the start point as already defined here. From the start point, move to the right, rotate counterclockwise direction. This should be θ3, but unfortunately this angle is not given. So this is one of the unknown. We have no clue how much is this one in the given problem. It is not provided. So it means that this is one of the first unknown, but you should understand that this θ should be variable. Why variable? Because it's going to change during the motion of this mechanism. How about R4? R4, it should be this one, the distance between C and B. And this R4 is a new thing to us through today's lecture. R4, it should be the distance between C and B. And this distance had been given as rho, which is the 300. All the time for this type of problem, this should be the radius, because simply point B is located over the circumference of the curve with the center C. So the distance between the center and any point belonging to the circumference of a curve, it should equal to the radius of that curve. It means that the R4 is going to be equal to rho, which is already given by 300 millimeter. It means that R4 is already given, and you should understand that it should be constant as we discussed before, that all the time this distance won't gonna change. Why? Because the slider slides over the curved surface. So all the time the distance between the slider and the center point, it is a fixed distance by 300 millimeter. But since the slider is going to slide definitely and point C is a fixed point, definitely R4 is going to change as direction. So θ4 is going to change, and also here it is not given. It is not specified to us where is the location of the slider. A very important notice here, probably the problem would be given to you somehow that you can see the point B is directly above point C. So if we set up the R4 in this case, and you try to specify the angle θ4, don't consider that it is 90 degree, where it is already in the drawing 90 degree, but we are not sure that this is the exact location at this instant of time. When this angle is 60, this should be the exact location of the slider. We don't know. So θ4, even though if the slider is already given above directly the center point, this angle should be considered unknown because we have no clue. There is no evidence that say that this slider or this angle, it should be 90 degrees. It means that the slider would be at any location. So when we solve the problem, consider just displace or move the slider either to the right a little bit or to the left, as I did here, like, or as already given as in this case. So theta 4, it will be unknown, and this is the second unknown to us. And definitely theta 4 is going to be variable. So as you can see, we end up with two unknowns, which should be these two angles. Definitely R1 and theta 1 should be provided. But it is not given. These R1, the distance between O2 and C, and the angle theta 1 also, which is this all the way angle, this angle, it is not directly given. But we can calculate this angle and R1 by doing some simple calculation. Simply, if we set up this triangular shape with a 90 degree, this triangular shape, you do have this R1 in the hypotenuse, and this distance is given by 300 millimeter, and this vertical distance definitely is going to be 300 millimeter. How did I know that this distance is 300? This 300 is already given to us here, right? Like this is the R1 in the given problem, and this is the triangular shape that I'm going to set up, right? So what does it mean? It means that this horizontal distance is identical to this one. But how about this vertical distance? It is not given, yes. But if this distance from point O2 to point C, it should be the same distance as this point. And this point belongs to the circumference of the curve. It means that this distance from this point to point C, it should be the radius of the curvature, which is already as well 300 millimeter. So it means that this vertical distance as well is 300 millimeter. Make sense? So from this triangular shape, if we did some calculations here, if we did some calculations, we're gonna end up that, I'm just gonna draw this triangular shape here. I do have this 90 degree triangular shape where this should be the position 1 R1, right? And this is 300, and this is 300, and this should be 90 degree. So simply, definitely this angle by definition is gonna be 45 degrees, and the R1, the magnitude is gonna be the 300 square root of 2 millimeter. Make sense? If we plug these things, so simply theta 1, how much is theta 1? Theta 1, it should be the angle from the start rotating counterclockwise, all the way, all of this angle, it should be theta 1. So all of this angle, it should be theta 1. So definitely theta 1 is gonna be the 270 plus 400 plus 45 degrees. So if we did the calculations, we're gonna end up with R1 at 300 square root of 2, and this angle, it should be constant. Why constant? Because it had been set up between, or this magnitude, it should be constant because it had been set up between two fixed points, and theta 1 is gonna be the sum of the 270 plus 45. This is gonna give us 350 degrees, and again it's gonna be constant. Make sense? Once we set up these position vectors and these things, your objective is just to proceed, solve like we did many times before, position, velocity, and acceleration analysis for this mechanism. Starting with the position analysis. Position analysis. In the position analysis, your objective is just to set up the loop closure equation for this mechanism. As you can see, we do have R2 and R3 are rotating in the same direction, but R1 and R4 in the opposite direction. So what does it mean? The loop closure equation is going to be R2 vector plus R3 vector on one side equal the R1 vector plus R4 vector on the other side. Make sense? Based on the thing that we defined up there, we do have the R1 is fully defined, R2 is fully defined, but R3 and R4, they do have unknown directions. So R2 is fully defined, R3 has magnitude but no direction, fully defined, has magnitude but no direction. As you can see, this is case number 4, right? This is case 4 of the position analysis. If you apply the case 4 procedure that we have to collect all the unknown vectors together, then we're gonna form R5. So if we did so, simply you can move R3 to the right hand side and move R1 to the left hand side, just to collect the known vectors in one side and the unknowns on the other side. If we did so, we're gonna end up with, we're gonna end up with this equation as R2 vector plus the R1 vector, negative the R1 vector, that it should be fully defined, and we do have the R4 vector negative the R3 vector. This one has magnitude, no direction, magnitude but no direction. Then we can combine these two into one R as R5 vector, which it should be fully defined, but we have to find this R5. This R5 is going to be the R2 vector fully defined negative the R1 vector, which is already fully defined. Then this is going to give us case 1. So we're going to work over this loop and solve for R5. R5, it has a known direction and magnitude. By solving this one, as we did many times, just decompose or rewrite again this equation into the exponential form, then collect the real part, connect the imaginary part. You're gonna end up with R5 will be, you're gonna get it by R5, we're gonna get it by the 409.92 millimeter, and we're gonna end up with theta 5, which is the angle of this position vector, as 148.62 degrees. And this R5 and theta 5, I mean this R5 position vector, it has been set up here or defined up there. This is the R5. R5, it should be, according to this equation, R5, it should be in the same direction as R1, because if you try to move R1 to be positive, so you're gonna find R1 plus R5 equals R2. So R5, it should be following the same direction of rotation of the R1, but opposite to the R2. So R1 is already rotating in this direction, so R5, it should be going up, as already defined here in the drawing. So this should be the correct direction of the R5, and you need this direction to correctly identify the angle of this R5, that it should be located in the second quadrant, as we got it here by 148.62 degrees. Once we find R5, you're gonna plug it here. You're just gonna replace this left hand side with the R5 that you located or defined as R5 and theta 5. So you're gonna end up with a loop recursion equation of just 3 vectors that belong to case number 4. Then you're gonna apply the procedure of case number 4 to find the unknown. These unknowns are mainly theta 3 and theta 4. After solving this or finishing the position analysis, you shall end up with the 12.95 degrees, and theta 4, it's gonna be 94 degrees. This is for the position analysis. Again, starting from this line, nothing is new. We just repeated the things that we did many times before. Once you finish the position analysis, simply you're gonna work over this equation. But after rewriting this equation into the exponential form, you're gonna work on the position, the velocity analysis, then the acceleration analysis of this mechanism to find the unknowns. As already given here, omega 2 is already given, and it is assumed that it is constant. It should be provided whatever it is constant or not. But since omega alpha 2 is not provided, it means that omega 2, it shall be constant for this mechanism. But it should be clearly mentioned to you that is it constant or there is a specific value for alpha 2. Anyway, once you apply the velocity analysis and the acceleration analysis, as we did many times before, you can simply solve the obtained equations in the unknowns to find the velocity and the acceleration of the slider in addition to point A. Make sense? So, going back again here to this problem. So simply we have formed this loop, right, or these different position vectors, and we did the position analysis, and we did the velocity analysis and acceleration analysis, and we end up with all the unknowns. But how about the velocity and the acceleration of point B? Velocity or acceleration of point B, it should be the absolute velocity and the acceleration of the point B with respect to a fixed point, right? In this mechanism, we do have two different fixed points. One fixed point, which is point O2, and another fixed point, which is point C already. If you decided to define the velocity and the acceleration of point B with respect to the fixed point, which is point C, this means that R4 automatically will provide us this velocity component and acceleration component of that point if we consider R4. But for some reason, if we are interested in identifying the velocity and the acceleration of point B with respect to point O2, it means that we have to set up a position vector here. And this position vector, it is not like R6. This R6, it is not necessary to be horizontal. It would be with any direction. And then we have to include this R6 in either this loop or the other loop to solve for R6 in case that the velocity or the acceleration of point B was required with respect to point O4. But definitely, in this case, there is no need to refer to point O2 since we're already referring to point C. And as we discussed before, R4, the derivative of this position vector is going to give us the velocity or component or components. In this case, it's just only one component velocity for the point B. And if we did derivative one more time, we shall end up with the acceleration components of this point B. Make sense? So this is for this example. Again, nothing new except the start of the problem. How you set up these position vectors, how you identify their values, which one is constant, which one is variable. This is the new thing. Then the rest of the procedure is the same as we did before for the analytical solution. Even in the graphical solution, as you're gonna, when we discuss the graphical solution method, you're gonna find it like it is typically the same as we did before. Okay? So now let us move, this is for the direct contact. Now let us move to the rolling contact. So we discussed the direct contact. Again, the key idea that we should have two objects. One is moving with respect to the other one.